Hello everyone, thank you for joining us for today's webinar on gemmology. I'm Ian Hayward, your host for today. With me are Tim Smith, our Raman Applications Manager from United Kingdom, and Riccardo Tagliapietra, Raman Sales and Application Specialist from Renishaw, Italy. We're recording today's webinar. We'll make the video available to you later. We have a lot of you in the audience, so I've muted your microphones to prevent confusion. But please ask questions whenever you like using the chat window on the right-hand side of the screen. We'll be answering your questions towards the end of the session. I'd now like to hand you over to our presenters. Ciao Riccardo, and hello Tim, who will start the presentation for us.
Thanks Ian for the introduction, and welcome to this Renishaw webinar about Raman microscopy and photoluminescence as tools for the gemmological lab. Before getting into the specific contents, in this webinar you'll see how Raman spectroscopy can be applied to quickly and easily identify gemstones, determine modification and imperfections for both the gem lab or for research purposes. We'll start by giving a simple overview of the Raman technique and some of the important considerations when analysing gem and geological materials. Important features of a Raman product for this application area and with the context of photoluminescence. Riccardo and I will then detail many of the commonly encountered scenarios faced by gem labs and researchers, looking at the identification of gems, authenticity and certification, inclusions, and fracture fillings. Raman spectroscopy works by shining a low power laser onto the material of interest and filtering the scattered light to contain just the Raman light. This light contains information specific to the molecular and structural composition from the region illuminated by the laser. This produces a characteristic spectral fingerprint from which the material can be identified. Being optically based, the Raman technique has some great benefits. These include being non-destructive and non-contacting, as well as not requiring any specific sample preparation. Chemical specificity is a real strength of the technique. The Raman spectrum is easily able to identify different materials unequivocally. Subtle differences, such as different polymorphic forms of the same material, where molecules have the same chemical composition but different crystalline structures, are analysed in the same way with the same simple and unique identification. Here is an example of different green stones within the pyroxene family. Jadeite, cosmochlore, and omphacite have similar compositions. Omphacite is a solid solution of jadeite, augite, and odurine. As well as producing Raman data, it is possible for some Raman systems to collect photoluminescence, or PL. Conveniently, this process uses the same laser source. This time, light re-emitted by the material is collected at any wavelength higher than that of the laser. The inVia Raman microscope is a single system combining both Raman and PL measurements together. Material identification is produced from the Raman information, usually in just a few seconds. The PL produces complementary information, revealing defects and inclusions. Together, these methods characterize gemstones and minerals. As we'll see, together this can reveal processes which may have been applied to a gemstone in order to artificially modify its look. So the inVia combines high-end optical microscopy, Raman microscopy, and PL microscopy together. From a microscopy perspective, we have high-resolution optical images, which support a range of illumination options, such as transmitted, polarized, and dark field. Dedicated holders are available to help quickly and easily hold samples in place for analysis. The Class 1 laser-safe system supports the use of low-temperature stages, such as those used with liquid nitrogen. This can typically benefit the PL analysis by making the spectral features sharper, simplifying interpretation. Sample positioning is performed using an MS-30 encoded high-speed stage. This has a 50 nanometer step size and can be used to generate Raman map data as well as the single position analysis. The microscope supports a range of objective choices, including high magnification, long working distance, and immersion options. This is important where analysis positions may be restricted or where liquid nitrogen is being used to cool the material. Regardless of the sample, we've thought about how it can be held in place in an easy way. Keeping the sample immobilized is important for the analysis to ensure the spectral data comes from exactly the point you want. Here we've got a stone set within a ring. This is held in place using an accessory kit. This is a really flexible approach for a large range of sample types. For samples which are a little larger, these can be analysed using a sampling arm. Here the inVia is being used to analyse a large sample which cannot fit onto the sample stage inside the system. Even in this scenario, we're still able to maintain all the performance characteristics of the system in exactly the same way as if we had the sample on the sample stage. We've seen how Raman and PL spectroscopies are combined together. Because these are used with a confocal optical microscope, we also have high spatial resolution in X and Y and high confocality in Z. Particles of 1 micron in size or smaller can be analysed as a result of this, and there is a lot of flexibility in the sampling volume. The inVia can be configured with different laser wavelengths. Typically, changing configuration is a completely automated process taking seconds. The use of different lasers enables the Raman information to shift to a different part of the spectrum if any strong fluorescence is a problem. It is typical for a green laser, such as 532 nanometers, to be used for most of the gem and mineral applications of Raman. Material identification is achieved using Raman libraries, which match the shape of the collected spectrum. Renishaw has a dedicated inorganic and minerals library, but supports third-party libraries as well. You can also build your own library if you've got a specific need, and this is all integrated into the wire software, which is used to run the system and analyze the data together. Using the MS30 motorized sample stage, we can collect map data from which force color images of the sample are generated. This enables spatial context of different materials, which may be present from any mixture. From the images, distribution and particle sizes can be quantified and compared between samples. Next, we're going to look at how we apply Raman and PL to a range of different samples. First, we're going to look at how we can go about and identify different unknown materials. Here we see a range of different stones and what the Raman spectra look like for the different materials. The combination of band positions for each spectrum is unique and objective. The Raman spectra are usually collected in just a few seconds for these types of materials. Where a gem is in question as to its true authenticity, even when presented in a final piece, analysis is performed in exactly the same way. Here, long working distance objectives enable stones to be accessed from 10 millimeters away or further. There are many materials that superficially have similar visual characteristics to diamonds. Here we take 3 examples. For each, we collect a Raman spectrum and then use a library search to identify the material. This produces unequivocal identification of the material without touching it in any way. Here we have cubic zirconia, diamond and moissanite. The diamond spectrum characteristically has a single main Raman band due to the presence of only carbon atoms and its highly symmetrical nature. This means that all the molecular vibrations are effectively equivalent within that material. Here we have a set of black faceted stones supplied from Raffaella Navalny at RAG. The same approach was used to analyze a stone from each different group. 3 very different Raman spectra are produced and the material for each identified. Group 1 was identified as a treated black diamond. The color of natural black diamonds results from the presence of inclusions such as olivine and hematite. treated black diamonds are far more common. In spectrum 1, we see the diamond band at 1332 wave numbers and the amorphous carbon at around 1590 wave numbers. The diamond bandwidth is increased as a result of the irradiation during treatment from 4 wave numbers to around 8 wave numbers. This information confirms the type of black diamond. Group 2 was identified as a feldspar with the characteristic doublet at 484 and 511 wave numbers. The additional band at 671 wave numbers is not ascribable to the feldspars, but characteristic of amphiboles. Group 3 was identified as an organic acrylate. Here we've used a 785 laser to reduce fluorescence from the spectrum, and this group is therefore a gem imitation. So let's take a look at how we can identify Raman spectra in the wire software. Here we have a spectrum from one of those black stones. The spectrum has several Raman bands below 1000 wave numbers, and this is typical of materials that are inorganic. We can identify this spectrum using library search. Here we're searching against the Renishaw inorganic library, and you can see the top hit is labradorite. This has a hit quality value of just under 0.9, with 1 being the highest value possible. And you can see here a large number of similarities between the Raman bands from the unknown and the library spectrum. There's one band here which you can see is not being well represented, and this is most likely because of the presence of an additional material. While most of this sample comprises of labradorite, we can actually use a mixture search to understand the presence of any materials there as well. We can do that automatically or actually manually through an interactive approach. I'm going to show you the manual method. I click on interactive and hit apply. So now we have a list of the top hits similar to what we had before, and we can add in that top hit. At that point, the residual is then searched against other spectra within the library. The residual here you can see has this Raman band still present, and the top hit for this is actinolite. We could add this in as part of our mixture. You can see now this is being really well represented, leaving us mostly with a low residual within our spectrum. So it's really easy if you've got just one material to be able to library search and identify that material, or whether maybe you've got a combination and you want to understand all the materials that might be present within the unknown. Next, I'll pass over to Ricardo to talk through more detailed examples of how gemstones may be treated or modified.
Thanks so much, Tim, for this introduction on the features that make Raman and PL spectroscopies so useful for the gemmologist. And thank you all for being here today and watching this Renishaw webinar. So using some examples, I want to show here the benefits of these techniques to investigate if a natural gemstone has been treated, or how to determine if a stone is natural or a laboratory grown one. So in this first example, we want to distinguish between natural and synthetic in emeralds using the Raman response of structural water. In fact, emeralds can contain two types of structural water, type 1 and type 2. The water is present in their channels. So working according to the C-axis stone orientation to standardize the measurement, Raman spectra in the OH region show the presence of weak but significant water vibrations in crystals. In hydrothermal synthetic diamonds, we see the presence of a single band at 3608 Raman shift, and this is due to the absence of alkali elements like sodium or lithium. In natural emeralds, instead, some concentration of these elements is expected, and this gives rise to two bands in the OH stretching region, and moreover, the concentration of these alkali elements can cause the inversion of the intensity of these two bands. Here, in fact, we bring two examples. An emerald from Zambia having a high alkali content, and an emerald from Colombia with a low alkali content, and we can clearly see the inversion of these two bands. So one additional information that we can obtain from this measurement is also the origin of the stone. With this slide, I start with treatments in gemstones, and this is the case of a black pearl. The black color in pearls can be either natural or due to treatment, and in this case the pearl has been irradiated. I report here the Raman spectrum obtained at 514 laser excitation in red color. Using the Renishaw spectral database and search software, we can immediately spot out the typical bands of the aragonite, with the main feature at 1088 Raman shifts, and then there is a band at 710, and then a crowded area in the low wave numbers region. There are two additional features, one at 1360 and the second at 1453 wave numbers, and these are the typical features of the amorphous carbon. The carbon is formed after irradiation. Diamonds are a big topic in the gemmological labs, so when in 1999 Laser Kaplan International and General Electric announced a new method for making permanent improvements in the color and brightness of some diamonds, I just can imagine the worry, especially because at the time the treatment was not detectable by standard gemmological techniques. So HPHT, high pressure, high temperature treatments reconfigure the lattice of the diamond, eliminating those defects that are responsible for the color. So this changed type 2A brown diamonds from MNO on the International Color Scale to DEF, so colorless or near colorless. And photoluminescence analysis has proved to be the best tool for detecting this treatment. Photoluminescence must be carried out at low temperature, normally using a bath of liquid nitrogen at minus 77 Kelvin. And this treatment is done only on type 2A diamonds, which have special characteristics like internally flawless or VVS, and with a weight that is important. As said, the photoluminescence experiments must be conducted at low temperature. In these conditions, in fact, the permitted transitions are limited in energy, and consequently the corresponding Raman bands are narrower. Different setups with liquid nitrogen can be used, as you can see from these two pictures, but what it is important is that the temperature is kept constant during all the measurement. For this reason, the stone has to be fully immersed in the liquid nitrogen, and the liquid nitrogen has to be refilled from time to time. You may also notice that during the measurement the stone can sit on a thermally conductive holder like a metal. In this table here I summarize the experimental conditions, but it is also to be said that every gemmological lab has its own recipe for the experimental condition, because the evaluation of the treatment is not only objective but it's also based on repeated experience on a series of certified standards. But generally speaking, we can say that a long working distance objective is needed. It can be a ×5 or it can be a ×50 long working distance, but what is important is that it works far from the liquid nitrogen. For the choice of the laser, it really depends on the spectral range that we want to study. For example, to detect the N3, the H4 and the H3 centers, which are at 415 nanometers up to 500 nanometers, a UV excitation should be needed. But it's also true that the vast majority of gemmological labs have got only one laser in the visible. So in this case, the best laser would be a green laser at 514 nanometers. This is better with respect to other green lasers like the 532 nanometers, because in this case the one of the analytical photoluminescence bands will fall under the very strong first order Raman band of the diamond, and this would hide the analytical band to detect the treatment. Moreover, it is important to have a system that can cover a wide spectral range at high resolution. As a matter of fact, the photoluminescence experiment can go from 500 nanometers up to 800 nanometers, and the resolution has to be high because the PL band at low temperature are quite narrow. So the initial Raman system with synchroscan can cover a wide spectral range at high resolution, and this is very important for this type of measurement. Here a report to spectra that were given to me by Maya Musa from the Gulf Institute of Gemmology in Muscat. These are two low temperature PL spectra of type 2A diamonds, and amongst the different spectral features we immediately notice these two bands at 574.8 and 637.0. This do corresponds to the NV vacancies, the uncharged one and the negatively charged one. So there are different variables that we consider for the evaluation of the treatment in this type of diamonds. Two of these are the neutral vacancies, in which we consider the ratio between the two, given here generic values, so untreated between 1.7 and 7.7 and treated between 0.3 and 0.7, but also we consider the width of the 637 nanometers band, which becomes larger after treatment. So the third and very important other spectral feature that we have to consider is the general radiation center, GR1, which has got a doublet in the untreated stone at about 740, between 740 and 744. After treatment, this one fully disappears. This is the case of a CVD, a laboratory-grown diamond, and it's of a major importance for the jewelry industry to distinguish between natural and laboratory-grown diamonds. And this can be done when bands from silicon-related lattice defects, CV, are present in the low-temperature PL spectrum. Silicon is in fact an impurity usually introduced during the CVD process, and it's not a common feature in natural diamonds. And these defects correspond to this doublet of peaks at 736.6 nanometer and 736.9 nanometers. Moreover, the general radiation center is absent in this type of CVD laboratory grown diamonds because they are also normally HPHT treated. Here is an example of a heat treatment in spinel. This is actually not easy to be detected using the optical microscope because the treatment temperature is not that high, just 800 Celsius degrees, and because the number of inclusions in this type of stones are quite limited. With Raman is instead very, very straightforward. I report here the Raman spectra of the untreated spinel in red color and in black color the treated spinel, and we can immediately see that the band at 406 Raman shift has an enlargement after treatment. If the stone is fluorescent at the excitation that we use, it is also possible to use the PL spectrum that can detect the treatment too. The analysis of the inclusions is very important for the gemmologist, both for treatment identification in color stones and for the origin determination. To study inclusions, high-resolution long working distance objectives are needed. So normally a times 100 with long working distance, but depending on the size of the inclusion, also lower magnification objectives can be adequate. Moreover, the Raman system must be confocal, and the Reynishaw Raman systems have got the unique feature called easy confocal to study small volumes. In this case, in this spinel inclusion in natural corundum pink sapphire variety, we have used a times 50 objective with a working distance of 8.2 millimeters. Also, the sample illumination is very important. So the inVia microscope supports transmitted, reflected, and dark field illumination, giving you a range of options for locating the inclusions. This example is an inclusion of spinel in natural corundum. Here I report in red the Raman spectrum of the inclusion, and in green color the match with the Renishaw Inorganic Materials and Mineral Spectral Library, which contains more than 1000 spectra of minerals. And here the spectrum of the inclusion in the corundum has been identified as spinel. As the next slide is a 3D image of an inclusion, I want to present here a slide that describes what Raman imaging is, starting from a 2D case on a mineralogic thin section of an ultramafic igneous rock section that shows hydrothermal alterations. So in mapping or imaging, the sample is scanned under the microscope objective, and an entire spectrum is collected for each sample point. When the spectral dataset has been created, we can generate from this a multitude of Raman images. These can be generated using univariate techniques. So for example, we can consider one band to show the presence of that molecule in that particular place of the sample, or the width of a band to describe the crystallinity of the sample, or a shift of a band to describe the stress in that material, or we can use multivariate techniques. Multivariate techniques consider all the band present in the Raman spectrum, like, for example, component analysis, which is the algorithm used to produce these images. And as a matter of fact, images of the different mineral components of this rock have been generated and superimposed to the optical image, and this is a cross-polarized optical image. So the benefits of Raman imaging are obvious. Raman imaging allows us to locate the presence of materials, to quantify the size, domain, and so on. This is maybe a more research-oriented example, but it is still important to show it here. So this is heat treatment in rubies and sapphires. These treatments are used to enhance the color and modify the clarity of the gems, and it's nowadays commonly accepted by the gem trade. In this study, we examined a zircon inclusion inside the sapphire. After the treatment, the inclusion is melted, altering its crystallinity and leaving a gas bubble in the middle. The bubble that is actually still is also visible in the optical image at the microscope. And this can be easily detected by micro-Raman spectroscopy volume imaging. In volume imaging, it is very important to work at a high resolution. So, depending on the size of the inclusion, a high magnification objective may be required. And if the inclusion is not immediately beneath the surface, and this one was about 500 microns below the surface, a long working distance objective may be needed too. So here we use the ×50 with a working distance of 8.2 millimeters. And we use the green laser, and we used a high resolution grating, a 24 lines, 100 lines per millimeter grating that provided the resolution of one wave number. The collection technique is called stream HR. That is an imaging technique that is optimized for the spatial resolution. And because a 3D image is made by stacking several 2D high-resolution images, the resulting dataset is composed of a massive number of spectra. In this case, we collected 2.9 million spectra. So we see here the optical image of the inclusion when illuminated in transmitted light. And we see now here the 3D Raman image of the inclusion. How did we build this? So from the data set, we extracted one spectrum that was identified against the Renish mineralogical library, and the extracted spectrum has been used to generate, using component analysis, the 3D image. In the region of the bubble, 2 additional bands were present, and this falls in the frequency specifics for the gaseous carbon dioxide. Once we have the 3D image, we can also study sections of the image, simply changing the section plane at different heights. And we can also use spectral variables to show chemical and physical properties of the sample that we are studying. In this case, for example, here we report the shape and size of the zircon inclusion, showing also in green color the CO2 bubble in the center. In this central image, we study the stress in silicon. Stress is normally monitored plotting the shift of the Raman band. A higher shift represents a compression, and it's highlighted here in white color. Here on the right hand side we have the study of the crystallinity of one of the planes of the inclusion. Crystallinity is normally related to the width of a band. The more is width, the less crystalline is the mineral, and in this case the lower crystallinity is represented in white color in the image. Another very important topic for the gemmologist, that is the identification of the fillers in fracture treatments. Fillers used to hide cracks can normally be of natural or artificial nature, and Raman is particularly adequate to study this because of its very high spatial resolution. I remind that the spatial resolution of a confocal Raman microscope can go down to 1 micron using a ×100 objective. So the microscope is an ideal tool to study crack fillings and understanding their nature. In emeralds, the mostly used crack filling materials are of organic nature, like oils or artificial resins or waxes. Therefore, the choice of the laser for the excitation should fall onto a near-infrared one, like the 785 nanometers. Never a 633 nanometers one, as emeralds contains chromium that will strongly fluoresce. But most of the systems installed in gemmological labs only have the 514 laser, so some fluorescence background is expected. As a matter of fact, the spectra that I report here have been baselined, removed using the Wire software feature called Intelligent Background Subtraction that uses a polynomial of the 11th order. Cracks are normally superficial, therefore long working distance objectives are not normally required unless the orientation of the stone does not allow to use standard ones. Here I report the overlaid spectra of the mineral in red and the mineral plus the filler in black color. It is clearly possible to observe additional bands due to the filler that I marked with these orange arrows. I also report here the Raman spectrum of the CH stretching region for this particular case. The presence of moderate intensity features in the aliphatic spectral region and the poorly structured features at 2900 Raman shift indicates the use of a natural oil, probably a cedral oil for this case. As last example from my side, I show here the spectrum, the Raman spectrum of a glass that has been used to fill a crack in a ruby. Starting with the 80s, cracks in rubies have been treated with glass to enhance their clarity. But in this way the fracture is not repaired and the resulting material is therefore fragile, an information that should be given to the jeweler settler. So commonly the used glasses contain lead that can be detected at the microscope like a flashing effect, or better using the chemical analysis. Starting with the year 2010 in Mozambique, glasses with no lead have been used to fill ruby cracks, and Raman has shown to be a very quick method to identify glass in ruby cracks. So I finished now. I leave the word to Tim, who will tell us about how to study objects that cannot be placed under the optical microscope. Thank you very much.
Thanks, Riccardo. We've seen how inVia can be applied to a huge range of different gemmological needs. If you can take your sample to the inVia, there are several different options for how it can be analysed. If you want to have a more portable option, we have the Virsa Raman analyzer system. This is a FiberPro-based system, enabling research-level spectral performance and supporting single-click laser changing. This is an ideal solution where portability is a key requirement to the user. The Virsa system can be used in the lab on small or large objects in a comparable way to inVia. It can easily be moved to other locations, and analysis can be conducted in a conventional vertical orientation or rotated for horizontal requirements. This includes white light viewing of the sample and the ability to track focus as the probe is positioned to analyze different regions of the sample and during data collection. So this product has great sampling versatility and portability while maintaining the high levels of spectral and spatial performance. So we've really seen the ability of Raman microscopy to produce detailed and objective chemical information, and how this can be used for simple material identification using established or user-created libraries. The combination of optical microscopy with Raman and PL supports the investigation of stones, which may have been treated or modified. This is a key requirement for certification and is a fast process to support high throughput needs. Inclusions can be characterized, enabling identification, but also determining mixed species and being able to generate 2D or 3D confocal chemical images. These images show spatial distribution and particle size of all the materials at the same time, And of course, this can provide valuable spatial context to the chemical and structural information. So a special thanks to Maya Musa from the Gulf Institute of Gemmology for all her time and effort contributing to the contents of this webinar. Also to Raffaella Navone from RAG Turin and Jean-Pierre Chalan from SSEF Basel for their contributions. Thank you for your attention.
Thank you, Ricardo and Tim. Let's now answer some questions. Attendees, please keep typing your questions into the chat window. If we don't have time to cover them all today, we'll respond to you by email. Now, on to the first question. I think this is one for Tim. The Raman spectrometer, and for doing measurements also of PL, you use lasers. Yep. Is the product eye safe? Can you comment on that, please?
Yeah, so we use a laser, as we've talked about in the webinar, to generate the Raman and the PL information. So within the inVia product, we can have a class 1 laser safe system. To do that, we have an enclosure, so that's all fully interlocked like any other class 1 system. We can also choose for that to be class 3B if we want to, and of course, in that scenario, we'd need to take the necessary protective measures with safety eyewear. So we've got both those options open to us, but I think using a class 1 setup is pretty typical of most use of the system.
Thanks, Tim. Now a question for Ricardo. In some of your results, a 514 nanometer laser was used. Why was that used rather than a 532 nanometer laser?
So I would say that the two lasers are quite equivalent, but for the gemmological lab, the 514 is preferable because most of the lab, they want to do HT treated diamonds. And this means that the PL analytical bands are used for the identification, which means that if we excite with the 532 nanometer laser, the first order Raman band will fall at about 572 nanometers. And this band is particularly strong, so it will cover the 574.8 nanometers one. So this is the only reason why I would choose the 514, but still PL in the gemmological lab is very important.
Thank you. And now one for Tim. What about refractive index? Can you collect the 3D mapping with the refractive index to avoid distortion of the inclusions picture?
Sure. So there's two ways really of trying to address the refractive index issue when looking at depth into a transparent material. The first thing we can do is try to take that into account. So using a conventional dry objective type setup, we can understand what the refractive index is of that material and try to factor that into the depth measurements. That still causes data collection issues potentially with things like having a reduced confocal performance as we go deeper into the material, having less efficient Raman data collection at depth as well. So using a refractive index matching oil is pretty standard for this type of work. This allows the refractive index to be matched. So the lasers originating from effectively within the oil, that's matched to the sample most of the time, certainly in a far better way than the air. Therefore, we're getting much higher performance with confocality as we go deeper into the material, much better Raman data collection. You can actually also get benefits in terms of reduced fluorescence effects, as some of that can be absorbed by the oil as well. So that's a pretty standard setup we use to really help that type of depth analysis for depth profiles and volume type work.
Thanks, Tim. And now one for Ricardo. Concerning the emerald results and the alkali content, is Raman spectroscopy more sensitive to that than XRF, or is XRF a better technique?
Well, I would say that the two techniques are absolutely complementary. The XRF is a direct quantification of the alkali content. What I shown in the example, it's the effect that the alkali have on the channel water molecules. Of course, we know that these alkali are especially the big ions are positively charged charged, and they do cause orientation in the polarized water. And Raman uses a polarized lasers for the measurement. So this is the effect that we exploit. So I would say the two techniques are complementary.
Thanks, Ricardo. And now one for Tim about laser wavelengths. Most of the discussion has been about 532, 785 and things. And one of the people asks, what about 266 or some of the other excitation wavelengths?
Yep, so the inVia can cover a vast range of different laser wavelengths. Most of these wavelengths are centered kind of close to the visible region. That's where most of the optics are operating within the system. We can certainly cover everything from the deep UV and the near UV all the way into kind of the infrared, so 1064, using different configurations of the instrument. In terms of the application side of that work, really there's two reasons you might want to start moving away from the visible range. One of those is fluorescence, and the other one is really to do with resonance. So if you can coincide the laser wavelength with the absorption and the emission of a material, then we can sometimes generate extra Raman data, resonance Raman data. And this is particularly strong at this point. Some materials can benefit from this. I would say in general, certainly most of the gemmological applications we talked about wouldn't necessarily benefit from that. There's some PL benefit. You can see PL from all those wavelengths above 266. Whereas as you go to a higher laser wavelength, then that's slightly restricting the PL region you can analyze over. And then the last one's to do with penetration depth and spatial resolution. So a lower wavelength laser gives you a shorter penetration depth, so you're not analyzing as deep into the material. That's often really useful for looking at really thin coatings, more to do with materials, I would say, overall. And as you increase the laser wavelength, then you start to look deeper into the material. So a range of things to consider, but the inVia can be configured with many lasers and it can be upgraded in the field as well. So if you've got a specific setup and then want to investigate some additional configurations, then you can do that too.
Thanks, Tim. And now one for Ricardo, talking about fillers. When studying organic fillers, especially in emerald or ruby, most of the time you have really strong fluorescence with 514 nanometer, but there's also a lot of noise with 785 nanometer, which will hide the signal of the filler. Do you have any advice on how to get better signal?
Well, there are, I think that most of the times we really need to play between the two excitations. The advice is always to look both at the DCH stretching spectral region and also the aliphatic region, because from the shape and the structure of the DCH stretching, we can have an idea of what type of filler it has been used. I was told by Maya Musa from the Gulf Institute of Gemmology that orienting the stone in particular ways, it helps getting a better spectrum. So these are all experience-based way of measuring the stone, but definitely the excitation laser choice is the best to use. Unfortunately, some of the gem lab only have green excitation, so they have to play with this only.
Thanks. And one now for Tim about the Virsa instrument. Is the portable Raman you demonstrated, the Virsa, can you integrate into an existing microscope to create a confocal system?
So the Virsa supports different probes. Those probes are in essence a microscope. We support what we call a bulk probe, and we support a confocal probe. And with that confocal probe, we can reach similar levels of confocal performance that we would be able to achieve with the inVia and in terms of spatial resolution. So in that sense, we're not looking to combine it to something to achieve that. We actually have designed those options to support it natively, depending on the type of work you want to do and the trade-off you want to have between spatial resolution and the analysis of kind of bulk type samples.
Thank you. And now here's a question, I guess, Ricardo first, possibly Tim, is do you have options for diode lasers for 633 nanometer and 532? I think 532 is available as a diode.
They are both.
The question, I think, relates to the longer shelf life of diode lasers over gas lasers. But if you guys would like to comment, perhaps Ricardo?
Yeah, definitely. I think that the comment is correct, and there are other advantages of diode lasers over gas lasers, and that it's the big cooling fan is not needed, which means that the laser is less noisy, and of course the life is longer. There are some reasons why we still want an argon ion laser, for example. It's because it comes with 3 excitation in the same laser head, which means that we have 1 laser and more excitation options, while solid state lasers normally emits a single band. But I would recommend diode laser nowadays.
Yeah, there's lots of options, isn't there, for lasers? And I think overall, you know, if you are unsure about which laser might be best suited for your work, then definitely get in touch with us, because you know we have such a vast range. I can understand why, you know, it can be quite overwhelming sometimes. But overall, I would say that the diode lasers often give us more options for the amount of laser power we can put down onto the material. So diodes often mean more laser power. Certainly those diodes and solid state lasers are now incredibly stable and really have reached the same level of performance as some of the gas lasers that we've had for a long time. So yeah, I think overall there's been a few questions about the different lasers, and it very much depends on the application and exactly how it's going to be used.
That leads me nicely on to the next question, which is one for Ricardo, and that is, can the laser power affect the results, for example, when analyzing inclusions?
Absolutely, yes. I mean, we know that we are concentrating in a very small volume a certain amount of laser power. So we have to consider the density of the laser power on the sample. So a good practice is always to start the measurement when we don't know the inclusion nature. A good practice is always to start the measurement from low power. Moreover, minerals normally are good Raman scatterers, so that should be enough to get a good spectrum. So absolutely, Raman is not a non-destructive techniques, but with we really need to pay attention on the nature of what we are measuring, on the size, and so yeah, definitely we need to keep in account of the laser power delivered to the sample.
I think we're now drawing to about the end and running out of time, so I would like to thank you, Tim, and I'd like to thank you, Ricardo, and thanks to you, the audience, for the questions. If you didn't get a chance to ask your question, you can still do so by going to bit.ly/AskRamanQuestions. We'll send a follow-up email about the recording and answers to any questions we didn't have time for. Our next webinar is entitled Raman Microscopic Analysis of Macroscopic Samples and relates to the Virsa that Tim touched upon. In this, we'll show you how to get Raman spectra from samples you cannot analyze under a microscope. Examples will include barrier-coated gas turbine blades, paintings, graphene grown on copper foil, and systems undergoing phase changes. We hope you can join us. Please look in your emails for info about the webinar, or go to runnyshaw.com/Raman-webinars, where we'll be posting information about the webinar very soon. So once again, I'd like to thank you all for being with us today.
Thank you.
Best wishes from all of us, and goodbye.
Thank you so much.